A very good afternoon to all of you. And as you know, in my previous video, I just gave an introduction of nanotechnology, and in that video, I told you that I'm going to make a series of lectures that will lead us to have some understanding of the physics that's linked with the nanoparticles. And to be precise, in that video, what I tried to give the gist of nanotechnology, tried to talk about the differences between the properties of the bulk matter and the properties of the materials which are designed, which are prepared at the nano scale. So, so to start this series of lectures, I hope that to some extent I'll be able to make an impact to the students, that they may find themselves in a good deep down situation where things might look to them as interesting as possible. So today, as I'll call it, the first lecture on nanotechnology, I'm going to start from the very basic concept of solids. So I'll be talking about the bulk materials, and as I said in my previous video, that for an electron to be in a bulk material, the electron will never see the boundary of this material. So that's the basic assumption, that any material where an electron will never see a boundary, you can consider that material as a bulk material. Now, the very first important thing is that let's go into the history of free electron theory. And free electron theory, we have two versions of free electron theory. One is the classical version, which is called the drug model, or it's also called as free electron gas theory. And then we have its counterpart in quantum mechanics, which we call as quantum free electron theory. So I would like to introduce you with the thing that we're going to discuss. So I'll be giving some important assumptions that are needed to describe these two theories, and try to compare the two theories as long as the explanation of these solids is concerned. So so this is what I said. I said that what we try to do is we try to understand that how electrons contribute to the properties of these metals. So the domain here is precisely the metals. We are not talking about the materials to whom you apply a potential difference across and there is no flow of current. We're not talking about insulators. We're not talking about semiconductors. We are talking about metals. And we have the two models, as I said. We have the classical free electron model. This is also called as drug model. And then in the quantum version, we have the quantum free electron theory. And this theory was introduced by Sommerfeld. Now, talking about the classical free electron theory, this was proposed by Drud in 1900. And what it does, basically, it treats electrons as free particles. So electrons are treated as balls. They are treated as tiny balls, tiny particles, like that of gas. And electrons move randomly. So there are random motions that are linked with electrons. And these electrons are assumed to be free within the metals. And that doesn't mean that these electrons can leave the metals, because there is a positively charged background that prohibits these electrons to leave the surface of the metals. So what we have, electrons move randomly and they collide with metal ions. And this is the basic approach of the classical physics. And the classical free electron theory. And you can presumably assume all the postulates of all the postulates of kinetic theory of gases. They're all applicable to discuss this classical theory of metals. So, what is the key concept here? The key concept is they behave like tiny balls. You have electrons, they are the balls, they hit each other, and they bounce off the fixed metal ions. As you have the positively charged background, in that background, all of these electrons live, they are treated as balls, and their motion is random unless an electric field is applied. Because as we know, the moment we apply the electric field to a conductor, there's a flow of current. So we can say that there is a divergence. There is a divergence from randomness of these electrons. Some of the electrons take part in the current that flows through this conductor. So this randomness goes down as you apply your metal with an external electric field. Now, talking about quantum free electron theory, this theory was introduced by Sommerfeld, and this theory was introduced in 1928. What electrons do, they obey the basic laws of quantum mechanics, and their energy levels are quantized, which is a contradiction to the classical model, because in the classical model, the electrons that we have, they have all possible energy as being the point balls in the classical domain. So the motion of the electrons, it's not governed by the classical perception. It's governed by the probability. So probability plays a very important role when we talk about the motion of the electrons in these metals. So the concept of the quantum theory, what's the basic concept that we take into account is that electrons do not move like balls. As I talked about, the classical version, we have electrons being treated as point balls, and here we don't have electrons like balls. They are wave-like, and what they do, they occupy discrete energy states. So electrons do not have all possible energies. They have energies which are discrete in nature. Electrons can have only some finite energies in those energy levels. So their behavior is described by the quantum rules. So here we have the wave-like domain that takes the lead role, and we talk about the probabilities when we talk about the quantum version of free electron theory. So if we compare the two, theories, in classical we have random particles with continuous energy. As I said, electrons can have all possible energies in these solids, in these metals. But talking about the quantum version, these electrons are wave-like entities, and they have some finite quantized energies. And to be precise here at this point, the classical physics, the classical theory basically fails to explain some of the important properties of these metals, and one among them is the specific heat, and another one is the conductivity. And quantum model provides accurate predictions. Even though the drug model is capable of telling us about why there is current in a metal when you apply the potential difference, there are a range of things that can be explained using the drug model. It tells us about the conductivity, but that conductivity it talks about is the conductivity at the room temperature, and it talks about the electrical conductivity, it talks about the thermal conductivity, and then it gives an explanation to widely known as Weidmann-Frayn's law, but what's basically the ratio between the thermal conductivity and electrical conductivity, which happens which happens to be proportional, to the temperature. So, in addition to that, the classical drug model is able to explain us the other two important properties of metals, like why metals have luster and why metals are opaque. So there are a range of properties that drug model is able to explain us, but when we talk about the other properties, like why metal is a metal, and because we have the other classes of solids at the same time, why an insulator is an insulator. So the classical drug model, it fails us to explain why certain materials are conductive in nature and why some others are not. And it fails us to explain the semiconducting behavior of certain materials. So, here we can say, in comparison to the classical drug model, the quantum version gives us more precise explanation of solids. So, the applications of these models, what they do basically, they explain us the electrical conductivity of the metals. They talk about the heat conduction in metals, and they are a foundation for semiconductors and modern electronics. So these models that we will be describing in their formal theoretical mathematical models, they certainly explain us these important properties of the metals. So to conclude this introduction, what we have, this classical model is simple, but it has limited applications. It does not explain the wide range of properties of these materials. And quantum theory gives a more accurate prediction and complete understanding of the electron's behavior rather than of solids in general, where we can be in a position to classify an insulator from the conductor. So this was the introduction. So what we'll be doing now is we will go with the drug model in this video. We'll be talking about the drug model. So we'll be talking about the drug model. So drug model. What we have a metal, and in the metal the electrons are free, and there is no interaction. There is no interaction between the electrons. Electrons are point balls. They behave exactly like that of an ideal gas. These are the basic assumptions that we keep in mind when we start tracking down the drug model of metals. So I think what we have is we have a conductor, and we apply the potential difference to this conductor, and when we do that, we have a current, and that current is because of the motion of the electrons, and the direction of current is always opposite to the motion of the electrons. So assuming this conductor having length equal to L, and it has an area equal to A. So if I talk about one electron, and I can think of calculating the force acting on the electron. So F is ma. Assuming that m is the mass of the electron and a is the acceleration. So this mass times acceleration is nothing but E and E. Because when we define electric field, it is force experienced per unit charge, Q naught, where this Q naught tends to 0. So this ma is equal to EE, and for A is the acceleration, and we know that acceleration can be defined as the time derivative of the velocity. So for the acceleration, I can use here dv by dt. And I can use the value of this acceleration in this equation. And for m, I'll write m. For a, I'm going to write dv by dt. So let's proceed from here. So what I have dv by dt equals e by m, where this E refers to the charge of the electron, E is the electric field that you're applying to the conductor, and M is the mass of the electron. So from here, we can calculate the velocity. We can calculate the velocity of this electron. And what's that? That's going to be dv equals E by m dt. So I can integrate this equation, and E by m E dt. I will start my time from 0 to t. So differential and integral will cancel, and I will have the velocity v will be equal to E by m, and this differential and integral will cancel t. So this is the velocity of an individual electron, and this velocity comes in action when you're applying an electric field to this electron, and this electron is assumed to be free within the framework of this metal. Now moving from here, so I will call this as equation 1 because we want to achieve those results that we perceive experimentally. And what we're trying to do here is we are trying to use the theory to explain the various properties of these metals. So I'll be calling this as equation 1. So my equation 1 is clear here. Now, what can I say about this electron? This electron has kinetic energy, and I can write down that kinetic energy as 1/2 of mv squared. And this electron has kinetic energy in the domain of kinetic theory of gases. This kinetic energy is 3 by 2 k, b, and t. Now, for this equation, m is the mass and v is the velocity. And for this equation, kb is what's called as the Boltzmann constant, and this capital T is the absolute temperature. And we can compare the two equations, and we can say that 1/2 of mv squared that defines the kinetic energy is equal to 3 by 2 kBT that defines the kinetic energy. So here we can see that this 2 and 2 will cancel, and I can think of writing to make my calculation simple, because what I want to obtain some results, the results that are experimentally taken, and I can compare those results with the assumptions of the drug model. So MV, I can write is 3 kBT divided by V. I can do this thing, okay? So this is my MV, and this, keep in mind, is V. Okay. Now, in actuality, what we have a large number of electrons that are free in the metal. They are not free as if they can go anywhere outside the metal, provided what's important here is that they are free, but they are free within the framework of the positively charged fixed background. Now, there is randomness, there is a range of electrons, and they will have collisions. And these collisions give birth to some of the important definitions. The very first definition is mean free path. Mean free path. Now, one electron has an interaction with a range of electrons that are in the vicinity of this electron. So the average distance that the electron will have, the average distance the electron will translate in the solid is referred as the mean free path. And once we have mean free path, and this mean free path, let's assume this is lambda, this lambda defines the mean free path, we have another important definition, what's called as relaxation time. relaxation time. And this relaxation time is symbolized as tau. And relaxation time gives us the measure of the average time of a collision between the two electrons. So the time that the electron takes to have a collision with another electron leads to what's called as relaxation time. Now, moving from here, so this is my lambda, this is my tau, this is my NV, and I have V that's calculated over here. This is the V for one electron. Now, obviously, I'm talking about the range of point-like particles which we call as electrons. There will be an average velocity of this electron. If I call this as V average. So V average can be written as integral of 0 to tau V dt divided by integral 0 to tau dt. And this equation will give me the measure of the average velocity of an electron in this metal in presence of the electric field. So we can see this equation is dimensionally correct, and for this I will get tau, and I can think of using V that I have already calculated. V I have calculated as, let's check that, EET by N. So I would like to use these results here. So I will have V average. This V average is going to be EET dt by M divided by tau, because this differential and integral will cancel and we will get tau in the denominator. So V average, I can write V average is E by tau N. And then I integrate T will give me T squared by 2. The limits will run from 0 to tau. So V average is going to be, it's going to be EE tau squared by tau N. And we can see this tau and square will cancel, and we will get V average equal to E tau divided by, I have missed this 2, divide by, it has to be 2 here, divide by 2N. So this is my average velocity of an electron living in this metal, but an external potential difference is applied across this metal. So this is my average velocity. Now, from the basics of the kinetic theory of gases, we know that the current density, and what's that current density? That's J. This J is equal to EnV average. So where J is called current per unit area, E is the charge of the electron, N is the number density, and number density means number of electrons per unit volume. And V average is already calculated. So I can write down this J as, it is a vector, so I'll be writing its magnitude, that is En. For V average, what I have calculated right now is EE tau by 2N. This is EE tau by 2N. This should be the case. So this is EE tau by 2N. Okay, so this is my J, and to define this tau, and tau is what? It's the relaxation time. It certainly has a link with the mean free path. Mean free path can be chosen as the distance divided by V. V is the velocity. So I can use this tau here in my equation, this will give me J equals En times, then you will have EE by 2m. For tau, I'll be using lambda by V. Now, if you go back and you see that this mv I had calculated, this mv it was 3kBt by V. This mv that we have calculated, it is 3kBt by V. So for this mv, I will be using this result that I have already obtained in this lecture. So moving on from here, I will have J. So J is equal to, okay, come on, E, and E will give me E square, and then I have N, then I have E, and then I have lambda divided by 2 is there. For MV, I'll be using 3kBt divided by V, that V will be multiplied here. So this will be my J, what's called as current density. So J is, this is E square N lambda V divided by 2 3s are 6 KB and T, and I'll keep electric field outside this parenthesis. And this term that is in the bracket, this is called the conductivity of the material. And that conductivity is symbolized as sigma. So I should write here, J is, if I write in vector form, J is sigma E. And this is nothing but Ohm's law. And sigma that we have, it's a constant, and this sigma is equal to E square N lambda V divided by 6 kBt times nothing. So we can say that this sigma this is the first important result of the Dredd model, that this conductivity is inversely proportional to the temperature. Okay, so this is electrical conductivity. You apply an external potential difference, and that potential difference leads to the flow of current in these metals, and you calculate the conductivity. You calculate the conductivity of your material, and that conductivity comes out to be equal to this. Now, let's go into another domain. So this equation is important for me because finally I want to obtain the Weidmann-Frey's law, which is basically the ratio between the electrical conductivity of the material and the thermal conductivity of the material. So this equation, I will call it, I'll call it the equation A for the time being. So this A should be in my mind. Now what we have? Now we have a solid, and this solid, if I think this solid has faces, and when we talk about thermal conductivity, I assume that the flow of heat is Q. This is the flow of heat. And this flow of heat for an ideal conductor is proportional to the area of the cross section. It's proportional to the gradient of the temperature, and it's proportional to time. And if we take out this proportionality, we introduce a constant K and introduce the negative sign that takes care of the direction of the flow of the heat, and K is the thermal conductivity constant, and dt by dx times T. Now, for the sake of simplicity, I choose my problem in which the area of cross-section is 1 and the time is 1, taking the correct form of the units to boil down my heat flow equation as Q equals to, taking negative sign away, K dt by dx. So this is my Q. This is my classical Q. This is the Q that we talk about. And this Q is K. K is a constant. It's a constant of thermal conductivity, and dt by dx gives us the measure of the temperature gradient. Now, moving from here, from the model of kinetic theory of gases, what we have Q equals 1 by 3 NE V lambda dE by dx. Now, all of the symbols are correctly known to us in this equation. The only thing that we have added here is dE by dx, and this dE by dx is the gradient in energy. It gives us the measure of gradient in energy. Because from kinetic theory of gases, we understand, since the electrons in a metal ought to be treated exactly like an ideal gas, so these electrons possess only kinetic energy. They don't have any potential energy, because what we assume is that there is no electrostatic interaction between these balls. There's no electrostatic interaction between these balls. So we are here only in the context of what we call as kinetic energy of these tiny balls. Now, so this E reflects that kinetic energy. And this E is 3 by 2 kBT. And we have written down this E, which is the only energy that is assumed in this model. That these electrons possess only kinetic energies. They don't possess any other kind of energies. So if I take the derivative of this equation with respect to x, I'll be getting dE by dx. That will be equal to 3 by 2 kB dt by dx. Okay, this is the case. So, very good morning to all of you. In fact, in my previous video, I was just talking about the classical treatment of I had subjected the metals with the classical theory, and classical theory is our drug model. And in fact, in that video, I did all the activities that I was supposed to do. And finally, when I returned back to the camera, I found that only half of the video was recorded. So the rest was gone. Anyway, it was okay. So I would like to continue it from the part where we had left when we were discussing the drug model of metals, which is basically a classical model that demonstrates some of the observed or some of the experimentally confirmed facts about these metals. So we'll be talking about this. What we had obtained in the last video was the conductivity, and the conductivity was equal to N E star V lambda by 6 K B and T. And this N is the number density, is the charge of the electron, V is the velocity, and lambda is the mean free path of the electrons, and Kb is the Boltzmann constant, and T is the temperature. This was our equation that we obtained for conductivity, and we could see this conductivity is inversely proportional to the temperature. And the another approach that we had gone to was the thermal conductivity. And in case of thermal conductivity, what we have obtained is we have obtained Q equals K dt by dx, and we were looking for another heat flow in view of kinetic theory of gases, and that Q is 1 by 3 N E V lambda dE by dx. So this is our equation that we obtained using kinetic theory of gases. When we discuss thermodynamics, the flow of the heat is given by this equation, and the symbols all have their usual meanings. But here what we have is the gradient of energy with respect to x. So if I look for this equation, and if I know from classical theory that the energy is 3 by 2 kBT. And if I differentiate this equation with respect to x, I'll be getting dE by dx is 3 by 2 kB dt by dx. So this will be our dE by dx, and I can use this dE by dx in my equation of Q. So for Q equals 1 by 3 NeV lambda, instead of dE by dx, I'm going to use that equation. So what I'll obtain here is Q. So Q is going to be 1 by 3 Ne, then we have V lambda, and for dE by dx, we'll be using 3 by 2 and kB dt by dx. And obviously we can see that we can cancel this 3 with this 3, and we'll be left with Q equals NeV lambda. So Q will be equal to NeV lambda by 2, and I think kB is there, and then we have dt by dx. So this is the Q that we obtain by subjecting the same problem to the kinetic theory of gases, and we already have this Q equal to k dt by dx. And with an approximation, with an assumption that the area of the cross section is taken 1 and the time of flow of the heat is taken as 1. So we can obviously equate the two equations that we have here. We can equate them, and what we'll get here, we will get k dt by dx is equal to 1 by 2 n, it has to be n, e, then v lambda kb, and dt by dx. And we can clearly see here this temperature gradient from the left hand side can cancel with the temperature gradient that we have on the right hand side. So we are getting an expression for thermal conductivity, and that expression is now K equals, so K is our thermal conductivity. This is 1 by 2 NeV lambda kB. This is our K, and we have already calculated sigma. And how much is sigma? Sigma is Ne squared lambda V divided by 6 kBT. So on the top, what we have the expression for the thermal conductivity, and at the bottom we have the expression for the electrical conductivity. These equations are obtained using the classical laws of physics. These equations are obtained by using those basic postulates of classical theory of metals, which generally imposes the assumptions of kinetic theory of gases, treating the electrons inside the metal as equivalent to an ideal gas, treating them as point masses, and assuming that between these electrons there is no electrostatic interaction, and between electrons and holes and a positively charged background, there is no electrostatic interaction. But to assume that that the system is stable, the electrons are inside the metal, we presume that there is a potential barrier by virtue of which these electrons cannot leave the metals. So what we can do here is we can divide these two things. So if I divide K with sigma, what I'll obtain, I'll be obtaining, this is K is 1 by 2 NE, then V lambda KB. Then we have divide by, now this divide will change into the multiplication, and I will multiply this. So 6 kBT will go on the top in the numerator, divide by NE square lambda V. NE square lambda V will be in the denominator. So there will be some cancellations. I think V lambda and V lambda will cancel, and N will cancel with N, and E will cancel with square, and then what you have, 2 ones are 2 threes are. So this is K by sigma equals, what we are left with in the numerator is 3, and we have KB here, and this KB and KB will give us KB square, and then it's multiplied by T, divide by, what will be in the division? We will have, okay, we'll have E, okay, we will have E. Okay, lambda is gone.